So we are now back after a day break between the class, and we will now talk about one of the most fundamental concepts in computer architecture. And this concept is being used in many other places in software development as well. It's called pipelining. Anyone heard about this before? The word pipelining. Can you raise your hand if you never heard about this, or like put whatever emoticons that you want to throw into the class? Come on, let's make it lively. All right, sad face. Okay, good start for sure. If you're if you're feeling depressed about all the work you got this semester, good news, P3. Okay, cool. I like that. P3 is easier than P1 and P2. I assure you. And one of your classmates who started confirmed me with that. Like, wait, that's it for the baseline. Yeah, actually a lot easier. All right, so we would learn about pipelining today. But before we go there, let me kind of do a quick recap, right? A quick recap about the lecture 3, which is single cycle architecture. And we've been talking about the downside of single cycle architecture, which is it has to be clocked, right? Your processor would have to be clocked because everything has to finish in one cycle. It has to be clocked based on whatever is the slowest component here. So let me assume this. Let me assume that if you do an add, if you would do an add, this thing takes 5 nanoseconds just because this whole thing would take 4 nanoseconds to finish and the rest of the component magically take 1 nanosecond. Right? So overall, the add instruction takes 5 nanoseconds. And somehow, if I said this add takes 4 nanoseconds, but if you have to do the multiply, it would take 14 nanoseconds. And these are random number that I came up with, but the ratio of how long this thing would take is somewhat in the ballpark, right? So in this case, if say my add takes 5 nanoseconds because the actual addition take it take 4 nanoseconds, and the rest of my circuit take 1 more nanosecond. How much time does it take for me to do the multiply? How much time does it take for me to do the multiply? If I say the adding part takes 4 and the rest of the circuit takes 1 more, and let's assume it uses exact same circuit to feed the operand into the multiply, but now the multiply instead of add, which take 4, now it takes 14. So in total, you're gonna take 15 nanoseconds to do the multiply, right? The multiply R0, R1, and R2. So if I say that I need to finish everything in one cycle, when I want to provide a clock for this CPU, if I want to provide a clock for this CPU, does my clock based on the speed of my adder, or is it the speed of the multiplier in this case? Multiply, right? It basically becomes like multiply is my bottleneck because I can't make it faster. If I make it faster, I cannot do the multiply because you will never get an output on time, right? So that becomes the bottleneck of the single cycle processor, right? Where if you want to change the state using your instruction from the program, from D1 to D1 prime, basically run an add, the data part, the slowest component becomes the bottleneck, which we call the critical path. So we can fix that using multi-cycle processor. By decoupling, basically, I just generate the clock. If add takes 5 nanoseconds and my clock is 1 nanosecond, how many cycles does it take to finish my add? So if my clock it clock every one nanosecond and add take 5 nanoseconds to finish. How many cycles do I have to wait until my add finish? What's 5 divided by 1? How many cycles would it need to take to finish this adding process? If add takes 5 nanoseconds and every clock cycle is 1 nanosecond, how many clock ticks do I need to wait until the add finish? All right, guys, wake up. What is 5 divided by 1? 5 cycle, right? So now add takes 5 cycle. That's multi-cycle architecture. So let's revisit, right? Let's revisit this. So if add take 5 nanosecond and clock is 1 nanosecond, then here the whole process would take 5 cycles. And now if I have to do the multiply, right? This takes 15 nanoseconds. So how many cycles do I have to wait until the multiply finish? 15, yes. 15 cycle, right? As simple as that. And that's basically our design. So what's the benefit over single cycle architecture? Let me ask you this. If my program is doing this, I want to do an add, then I want to do a multiply, and then I want to do an add, right? Single cycle, multi-cycle. So this whole thing, if I use a single cycle, oops, sorry. Did it just delete everything on this page? All right. Sorry, I hit the wrong button on my PowerPoint. So this is 15 nanosecond. This is 15 cycle. So if my program has to do an add, multiply, and then add, right? And then I want to say, how long does it take for me to finish in single cycle architecture versus multi-cycle architecture, right? So let me go with the easiest one. The multi-cycle architecture, how many cycles do I have to wait until I finish this 3 instruction? How many cycles does it take to finish the add in this case? So the first add would be 5 cycle, yes. And then the multiply is 15. And then the next add is 5, right? So in total, this is 25 cycle. How many nanoseconds is that for 25 cycles? That's basically 25 nanoseconds, right? Okay, so how many cycles do I have to wait until I finish if I use single cycle architecture? And this is a slight trick question here. How many cycles for the single cycle architecture? The keyword is single cycle architecture. So every cycle I finish 1 instruction. So how many cycles do I have to wait? Sorry. Okay. Let me re-explain this because you said it's confusing. Well, hopefully the new explanation helps. Now let's assume I have a program with 3 instructions with me so far. Basically, I just need to finish this 3 instructions. Right? And what I'm trying to do now is I want to compare the performance of 2 CPU designs. The first design used single cycle architecture. The second design used multi-cycle architecture. All right, with me so far. Basically, I have CPU 1 that use single cycle, and then CPU 2 that use multi-cycle architecture. And you want to buy one of these CPU. So you want to measure which one is better. All right, with me so far? All right, cool. So one easy thing I can test which one is better is this. I'll ask how many cycles does it take for me to finish these 3 lines of code, add, multiply, add, right? So how many cycles would it take for me to finish in CPU 1? Oh, start growing. This is number of cycle, and then time it take per cycle. So it takes 45 nanoseconds. The reason why is that because it's single cycle architecture. Every cycle you finish one instruction. So in the end, it does take only 3 cycles. Right? In CPU 1, because add take 1 cycle, multiply take 1 cycle, the third add also take 1 cycle. With me so far. Then for CPU 2, how many cycles does it take? For CPU 2, I already said 1 cycle is 1 nanosecond. So an add would take 5 cycle, right? The first add take 5, the multiply take 15, and then the third add take 5. So in total, this is 25 cycles. Are you with me so far? All right. So CPU 2, 1 cycle is 1 nanosecond. CPU 1, 1 cycle is what? 15 nanosecond, because I have no way to clock it. Because there's a multiplied right there. So 1 clock cycle would take 15 nanoseconds. Bad, right? So total time, CPU 1 takes 45 nanoseconds. CPU 2 is 25 nanoseconds. Which one is a better CPU? Which one is a better CPU? Yeah. Oh, where did the 5 come from? Okay, sure. The CPU is better. So that take care of the answer about which one is a better CPU. CPU is better in this case, in this context, right? There's a question, where did 5 come from? Because add take 5 nanosecond and each clock is 1 nanosecond. So I wouldn't have to wait for 5 clock cycles to finish one add. So that's where 5 come from. So is that clear? All right, cool. So another question is information about the cycle for the add and multiply. Are those given in the CPU? So if you go buy your chip from a computer store, you will not see that. But we know underneath, right? If you read like a detailed spec sheet from Intel, somehow they said that, like how many cycles does it take to do X and Y and Z. For example, you can actually check out. Everyone remember our old friend caching, like L1 cache, L2 cache? Remember those from System Skill? So if you go and check out the spec sheet, they actually list out how many cycles does it take to access the cache for each CPU. So you can actually check, hey, oh, if I go and access the CPU, it does take 4 cycles to go to L1, 10 cycles to go to L2. So these things are actually in many cases, listed on the processor. Some of them are not listed. Sometimes these like really small detail, like how many cycles does it take to add, sometimes it's not there. Sometimes it's not there. The reason why they're not there is, surprise, modern processor, um, the component that make things slow typically are on the memory side of things, the cache, right? You want bigger cache, you want bigger memory. The compute side, it does to some extent. Okay, great question. Is everyone CPU cycle 1 nanosecond? So everyone remember that when you read CPU spec sheet, or if you read CPU spec sheet, it comes with like gigahertz. Can someone tell me what's the sample of your CPU? How many gigahertz is that? All right, 4.4 gig. That's a fancy CPU. So let's say you have a 4.4 gigahertz CPU. How much time is one cycle? Anyone remember the formula from like physics when you change from hertz to nanosecond? Anyone remember that? How do I do this math? I want to change gigahertz to nanosecond. Yep. Time equal 1 over frequency. Your frequency is 4.4 gigahertz. So time is going to equal to 1 over 4.4 multiplied by what giga? 10 to the 9, right? So this is something along the line of, I would say, close to basically like 2.2 something nanosecond. 0.2 something nanosecond. This is a really fast CPU. Yeah, yeah. Within about 0.2 something nanoseconds, something has to finish going from one place to another. Yeah, Intel does support up to 5 with, yes, 0.227 exactly, right? So that's how fast is one cycle. And Intel chip does support up to 5 gigahertz, yes, right? So when you're not using all the CPU, one thing Intel chip can do is what we call turbo boost. Turbo boost is basically, okay, I know the CPU 1, 2, and 3 are not being used. I'm gonna increase the clock of CPU 0 to 5 gigahertz because I want to make sure whatever is running on CPU 0 is really fast. So you can do that, right? There are many tricks that the architecture community basically put together to make sure your CPU is really fast. Yeah, actually, I'm not sure about the number nowadays. Yeah, 7 seems possible, but it's probably really hard to overclock that far. And then by that point, your chip might be like melting. So, um, yeah, it does sound risky. So one thing that is risky about overclocking is what? What can go up when you increase the clock speed beside power? So let's say you increase the power consumption. Temperature, right? So when temperature goes up, what happened to things? It melts, right? It melts, and what happened is your CPU lifetime is gonna reduce. Uh, anyone try to overclock and somehow when you boot the machine, it doesn't boot up. It's just really close itself down. Like you overclock too far and the temperature go up too much, and then somehow everything power off. Anyone happen to that? Or like when you run a game, right? And your GPU is really hot, and then somehow your machine just restart itself. Anyone had that before on their laptop? Like playing games and things get, yeah, blue screen. To be honest, your motherboard and the CPU in these days and age also comes with like a temperature sensor that detects the temperature. And if it goes too far, you can run into that where the CPU just power off because it's know that hey, something's wrong here, it's too hot, right? Undervolts CPU is also okay too. You can save power. You can make sure your battery lasts longer. Your battery can actually then last longer, and that actually happened a lot with a mobile phone, right? If you buy a phone, surprise, these things get regulated so that your phone would last as long as possible. So these are many tricks that we as a hardware architect do to build, right? And work together with DOS compiler and many things in a way back end, right? We always talk about front end and back end. We are like back door in the back of the building. It's like back of the back of the back, right before you go to circuits and go to material science and physics. That's how far back end we are, right? But yeah, these are not magic. These are science. Surprise. So yeah, 4.4 gigahertz take 0.227 nanosecond. So that's a great question. Awesome. All right. Any other questions that are hopefully satisfy your curiosity? I love, by the way, I love this discussion. Oh yeah. So battery can melt too. Not a good thing. Yeah, that's also dangerous to both you in terms of the toxic health, I mean the toxic material as well as the environment. So yeah, Thai weather can do that. We get extreme heat. Yep. Um, especially March, which is right now. Yeah, they were not good thing, battery fluid. Also for lithium ion, they can caught on fire and explode it. So please be careful with a lithium ion battery, guys. Anyone seen like those exploding? Like the battery from like phones and things like that. Yep. I don't want to name the brand, but you've seen the news, right? So yeah, if you don't kind of control how lithium ion works, that can also be the catastrophic, like really bad thing that can happen. Um, yeah, hopefully we control temperature and every other things. Okay, so let's move on. By the way, keep the interesting things coming on the chat. I check this, so I'll address it. But in the meantime, also let's move on to now that we have the hardware design, right? In the multi-cycle architecture, when you fetch, do you actually use every other thing on the hardware? When you want to just fetch the instruction, what component is active? The program counter, the wires that connects to the memory, and the memory is active because it had to fetch that line of code. Everything else is not active, right? Why are you doing the decode? You're not fetching anything. The ALU is idle. It's not adding. It's not multiplying. Your decoder is trying to figure out, okay, what is this instruction? When you execute the add or the multiply, everything is not active. So let me ask you this question. While multi-cycle architecture is better, can we do better than this? Anyone think that, hey, maybe we can use all the components at any given point in time? Would that be good? Let's say I'm doing the I'm adding something. At the same time, the fetch is now fetching the next two instruction in the future. Decode is basically decoding my next instruction. Would that be a better design? So obviously that's a better design. So the question we want to ask is like, when many things are idle, right? What if we can keep pumping different instruction into the idle parts? So what are we trying to learn now is the techniques that from multi-cycle, which do add in 5 cycle, multiply in 15 cycle, and another add in 5 cycle. So in total, how long, how many cycles does it take? 25, right? Cycle per 3 instruction. So you run 3 instruction, it takes 25 cycle. We are now proposing a design called, we're gonna pipeline this in a way that, let's say you need to run 1 million instruction, like it's a really long program. Actually, it's not that long. 1 million instruction is not that long. We want to run 1 million instruction, and I would like to take 1 billion cycle. Would it be a lot faster? On average, I finish 1 instruction every cycle. Is this a better design? It's a yes and no question. Is this a better design? Somehow, if we can magically make this true, is this a good goal? Instead of 25 cycle to finish 3 instruction, I can do 25 instruction in 25 cycle. Way better, right? Surprise, your CPU now does this. CPU do the technique called pipelining, and this actually apply to CPU, GPU, and most hardware design. So what is pipelining? To understand pipelining, I'll go use a different example, something that's closer to all you guys have, basically all the things you have to do. How many people here do laundry before? So we all done laundry, right? And I love this example, to be honest, because when I took the class at CMU, my teacher, his name is Professor James Ho, he actually used the same example, which we all did laundry before. So what do you have to do when you have a pile of laundry? What do you have to do? All right, we need to first wash the clothes. Right? In the washing machine, let's assume we have the washing machine and dryer. Then we dry it. And then we would fold if you are a like neat person. Well, I mean, yeah, guys, either hang your clothes or fold it. Like, don't throw it in another pile. Um, yeah, so exactly, right? You would first throw them in the washing machine, then dry it and fold it. That's like a strict steps. What would happen if you first do drying, then washing and folding? It wouldn't work, right? And can I do this in parallel? Can I do like wash and dry and fold together at the same time? No, right? We don't have time machine. You can't do that. So you have, let's say you have 5 batch of clothes. You have one washing machine, one dryer, and your washing machine takes 30 minutes per batch. Dryer take 1 hour. And moving between one component to another takes no time. And folding takes 30 minutes. How long do you have to spend to finish all this thing? How long do you have to spend to finish doing this task of washing these 5 batches of clothes? All right. I'll give you maybe 3 minutes to draw it. I mean, if you want to just compute that on your head and give me the answer. How long does it take? All right. I'm gonna give you until 2:41 p.m. to finish. All right. We'll come back, and if you have the answer already, awesome. Otherwise, we'll do a quick like calculating the time it takes to finish this. If I'm a really uh lazy person and I haven't washed my clothes in a long time and have now 5 batches of clothes to clean, how long would it take me if I have one washing machine and one dryer? All right. All right. Anyone got the answer? I know it's not 2:41, but it should be 700 minutes. How many hours is that? Wait, that seems odd. It's not divisible by 30 minutes. It's divisible by 30. But I think you're at the right track. I think you just assume that 1 hour is 100 minutes. Am I right? So let's do this together, right? If you do the most obvious thing, wash, dry, fold. And then once you finish folding the first batch, you wash, dry, fold another batch. That's kind of like a multi-cycle architecture. And that would take how many hours? Each batch takes 2 hours. So it would take me 10 hours, right? So we have 5 batches, 2 hours each. So if you do it blindly without pipelining, it takes 10 hours. Can we do better? Yeah, that's 600 minutes. Sorry. So 10 hours, basically 600 minutes, right? But can we make it faster? What can you do? So let me ask you this. Can we make it faster? I want to finish this whole thing in less than 10 hours. Is it possible? Yeah, exactly. Exactly. You got it correctly. And that's pipelining. That's it. That's the concept behind pipelining. If I'm not washing, I put my clothes in the drying machine. The washer is not washing anything, so I put the new batch into the washing machine. So that's how, right? So batch number 1, number 2, number 3, and again, PowerPoint is fighting with me on drawing these things. Number 4, 5. All right. You would first wash. Okay. I would use the letter W for washing, D for drying, and 4 for folding. Right. So you do wash. Then you dry, take 1 hour, right? And then you fold. So this is time, right? Time. For the second batch, you can start right here because the washing machine is free, right? Then when can you dry this? Right here, right? That's when the drying machine is free, and then you fold it. Again, you can again wash. So for the third batch, you wash it right here, and you wait until the dryer is free, and then you fold it. Wash again, dry here, and then fold it. Wash, dry, and then fold. So how long would that take, right? Each small box is 30 minutes. The big box is 1 hour. So this is 30 minutes, 1 hour, 1 hour, 1 hour, 1 hour, 1 hour, and then 30 minutes. So in total, now it only takes you 6 hours, 360 minutes, right? How much time did I save here with pipelining? How much time did I save? I saved 240 minutes, right? I know it's afternoon. Do the subtraction is taking time. So I save a lot of time, right? And this works the same way in processor design. This works the same way in processor design. So we can pipeline in the processor as well. So now I'm gonna use the same terminology that we've been using so far, the steps that we have to do in process one line of code. So what's the first thing we do? We would fetch, right? We fetch the instruction. What's the second step? What's the second step after we fetch? Yeah, we send that to the decoder. So we call the second step decode, right? Actually, there's a reason why I draw my diagram this way. Because once I'm done with the decode, what do we have to do? I execute the code. Then if I have to go access the memory afterward. So that's the fourth step. That's the fourth step. Then once I'm done, I call this step write back. This is basically when I store the result, right? This is what we define as a classic 5-stage pipeline. So this is called 5-stage pipeline. If you get curious and checks out textbook in computer architecture, this is like one of the most classic pipelining stages that we have. 5-stage pipeline: fetch, decode, execute, memory, and write back. To your surprise, modern day processor, we go 30 different stages or more. There'll be multiple fetch, multiple decode, adder would get sliced into different chunks, multiply would get sliced into different steps. To access the memory, there's also multiple steps, and then multiple steps to write back. The reason why we do this is want to get as close to finishing one instruction at every single cycle as possible. Everyone with me so far? We are now going to pipeline my design that I draw here into 5 stages so that I can put in new instruction at every single cycle, right? So let's say I have instruction number 4 right here. Pipelining would dictate that I can then decode instruction 5 right here, fetch instruction 6, and in the meantime, instruction number 3 would be in the memory stage, and instruction number 2 would be in the write back stage. And each of these dotted line is one cycle. So one cycle, we move from 4 to memory. Instruction 3 from memory, we go to write back, right? So the next cycle, instruction 2 is done. Instruction 3 is here. Instruction 4 is now move here. Instruction 5, move here. Instruction 6, move here. And then you fetch instruction 7. Right? Every single cycle, what have we done? So what is the speed of this CPU? How many instructions can I finish in a cycle? How many instructions can I finish in a cycle? One. Yes, I can now finish one instruction every cycle. So let's put that as our goal, because it turns out some of these components takes longer than one cycle. For example, you go to the memory, that can take a while, right? But we'll keep that assumption as we have the magic memory. We go use the memory is one cycle. We multiply one cycle. So now we are running your CPU at one instruction per cycle. One instruction per cycle. And because it's magic, right? Yes, that's a great question. This seems like a dream for deadlock. And we'll talk about this in, I think, about 15 more slides or something. It's actually coming up. Great question. So we'll talk about that. But let's talk about some key issues first. So here are the key issues. If I'm handling different instruction in each stage, right? Execute is handling instruction n, decode is n plus 1, fetch is n plus 2. What does this mean? It means that my design, my CPU somehow have to memorize 5 instructions at the same time, right? Where I'm doing instruction n at fetch, n-1 decode, n-2 in execute, n-3 in memory, n-4 in write back. And the one that the programmer see, if I'm coding something in assembly and I run it on the CPU, I will see what happened after I finish write back, because that's the programmer visible state. That's when I finish running this instruction. It had to finish write back. All right, so you have to update, right? You have to update the register file with your output and update the program counter at write back. But somehow you have to store these intermediate values, right? Somehow you store this intermediate value. Anyone get confused so far? Because I want to make sure this part is clear. Anyone confused? Raise your hand. Don't worry, just let me know. All right. Okay, so let's assume this is a long, big pause with no comments on the chat. So let's assume that this is somewhat clear, that we have one set of register file. We don't magically have multiple register file, and you have multiple instructions on your pipeline. Your programmer has to see what happened after write back. That's when you update the register file, right? But then I need to somehow store any intermediate value. So I'm going to go back one slide. And show you what do I mean by that. I'm going to go back one slide. I'm sorry. Here on our design. So let's say instruction in the write back is this, right? I do add 0, R1, 2. So basically now R0 is 10, R1 is 20, and then R2 should be what? After I add the two numbers together, it should be 30, right? Somehow after this, R2 in the register file, which is right here, should take the value 30. Should take the value 30. And let's say this instruction I do add. I do this. Add R1, R5, and R2, which basically means that I have R1 is 20, same value. R5, let's say it's 5. R2 is now what? 20 plus 5, that's 25. I have two different instructions. You see the problem here. I have two different instructions. Both want to change R2. Both want to change R2. And now I have to make sure R2 is updated at the end with this exact order. With this exact order. So let me ask you this question. How do I store the value of R2 right here in the memory state? You see the problem here? Right. Anyone get confused? Anyone confused so far? I somehow have to remember multiple versions of R2. None of them is updated in the register file, right? So where do I store them? Can I store them anywhere right here? Because I just have wires. Can wires store information? No, right? No. So that's our big issue, because I somehow have to remember right here, the new R2 supposed to be 25. And then right here in this wire, the new R2 should be 30. Both are trying to update R2, but same wires, two different values. Impossible. Break all the law of physics. We can't do that. All right. Now let's make it possible. Let's make it possible. How do you propose? And any proposal here on what can we do? Yeah, we just insert a temporary variable that would store the value of R2 that is the result of each instruction. All right. And we have the name for that. It's called the pipeline register. Pipeline register. Why do we name it that way? What does register do? Register store value. Do we name it pipeline register because it's storing any temporary value that happened because of pipelining? So the goal is we want to store all this intermediate value that we don't expose to the programmer. We want to store this in the middle value. We are still computing, it's still in the pipeline, but we haven't commit or finished it yet. We want to save the state of each instruction through the pipeline, right? The goal is we add this pipeline register to store the state. One for fetch, one for decode, one for execute, and one for memory. And each of these would store any internal data related to that instruction in that stage. So let's say instruction N is in execute, N plus 1 is in decode. So you have one set of pipeline register to store N plus 1, anything related to instruction N plus 1 in decode, anything related to N in execute. And this can be quite costly, to be honest, because you have to store a lot of intermediate values, all right? But again, pipelining seems like an awesome idea. Who wouldn't want to make sure you can run one instruction per cycle, right? Who wouldn't want that? It's performance versus the cost of building the chip. So let me tell you what's the performance gain. Can someone tell me how fast is your chip? Again, 4.4, anyone? I think 4.4 gigahertz, right? If I can do pipelining, so I got one instruction per cycle. I got somehow do this pipelining magic. I now got one instruction per cycle. What's the number of instruction I can finish in 1 second? I just let my computer run for 1 single second. How many instructions can I finish? Can someone do that math for me? I have a 4.4 gigahertz clock. I can do one instruction per cycle. I give my computer 1 second to run something. How many instructions in assembly can I finish? So a quick hint in here, one cycle is 0.227 nanosecond. So what's the equation that I can do to get the number of instruction in 1 second? What do I divide with? So I have 1 second. Each of those, I can finish one instruction every 0.227 multiplied by 10 to the negative 9. I can do that many instructions. So can someone give me the number of how many instructions can I finish? Anyone get around 4.4? 4.4 billion? Is that a lot of instruction? Yeah, 4.4 billion instruction in 1 single second of your CPU. Basically, your CPU that can run at 4.4 gigahertz. If you can assume is 1 instruction per cycle. You are actually finishing about 4 billion instruction in a second. And to be honest, it's actually way more, because these days you can finish roughly 3 or 4 instructions in a cycle. In a cycle. If you program it well, then you can finish basically 12 billion instructions, right? If everything hit in the cache, it can be that fast. But again, your computer can be really slow in a lot of cases. So I'm gonna go on a tangential direction here, but some like, yes, if you buy anyone buy Cyberpunk and play, I haven't done that yet because I know it's really like by launch time it's like not optimized. Like sometimes your program is slow, right? So what are the source? What are the typical culprit of why your program becomes slow? Anyone want to give some example of things that can happen? How many people use too much memory and it run out of your computer run out of memory and everything becomes really slow? Like open like 10 tabs in Chrome and it gets slow and slow and slower. So if you have that, right, data access takes a lot of time. The memory stage, right? Yeah, so if you use too much memory, we call this oversubscription. Oversubscription means that basically I'm trying to demand the resource more than I have. So in that case, your computer would get slower and slower and slower, right? Yeah, you malloc a lot without freeing. That's also another thing that can happen, right? So over here, let's go back to our pipelining. Ideally, this is magical, especially if you have this magic 1 cycle memory. So that's why I say, hey, memory is always like one of the primary thing you can blame, because yeah, there's no such thing as 1 cycle memory. I can tell you that. Even the L1 cache, if you look at the spec sheet, it will take 4 cycle. So ideally, the CPU has to be designed to get as close to this as possible. And we will learn in this class actually how it's done. Like we will learn how this is done. Let's keep again the goal at a cycle. All right. So now notice how I have this like block, vertical block here. So these are pipeline register. So these things are pipeline register that I use to store each version of the data local to each instruction. Let me give you the example of the previous add thing. Over here, I do add, right? 0, 1, and 2, where 0 is 10, 1 is 20, and 2 is 30. Over here, I do add 1, 5, and 2. So over here, 1 supposed to be 20, right? Because it has to be the same value. 5 from my example is 5, so 2 is now 25. Let me ask you this. At this point in time, which if I look at this pipeline register, right? What is the value here? Oops. What's the value of the wires here that's about to go to the register file and replace R2? What's the value that you should see? At this point, that is specific to this instruction adds R0, R1, and R2. What should I see in this value? So let me give you 2 choices. Should I see 30 or 25? this should have the value 30, right? This whole thing should have the value 30. If I look at this, data coming out of my adder and store in this, again, pipeline register, so what should be the value here? The value that's local to this instruction, right? In this case, should it be 25? Should it be 30? Which one should it be? It should be 25, right? Because that instruction in the memory stage has the result of 25. You're adding 20 and 5 into R2. So the wires that come out of that pipeline register should reflect. It should reflect that instruction. All right. Any questions so far? Any questions so far? All right, so if there's no more question, how about we take a quick break and resume at 3:11? Let's do a 5 minutes break, all right? Should we do that or should we move on? Yeah, let's do a quick break. We'll resume at 3:11 p.m. All right. Okay, cool. I'll go make coffee. So I think I need a quick break as well. Here. So, wait, did I resume the recording? I did. Okay, so one of the multiple questions, because again, we are designing the hardware, right? We can keep adding more stage. That's one example that's done in many, many modern processor. You can go up to 10, 20, 30 if you want, right? The reason why, so what's the benefit? Let me ask you this. If I have a design that a 5-stage pipeline and say I want to have, instead of 5 stage, I want to go to 10 stages. What can be the benefit? The reason behind it is like I can have a faster clock, right? I can have a faster clock. And that's actually one of the classic techniques on getting the clock to go faster. Why is that the case? Basically, if you go one distance, it takes one amount of time, you half that distance, clock gets faster because now your electron can move from one point to another in a much quicker manner. All right. It also enabling more structure to be active at all time, right? You get higher utilization. So what's the downside of adding more and more stages? Consume more power, more die area, more complex to design. And what if there's a branch, right? We haven't talked about branch yet, which is if else. If else. We haven't talked about that, so we'll keep it at that. And let me first ask this question. Let's ask, like, okay, let's have the actual instruction and with pipelining, with this magic 5-stage pipeline with the magic memory, how many cycles does it take to run this 4 instruction? So I'll in the table below, I'll use F for fetch, D for decode, E for execute, M for memory, and W for write back. All right. So instruction 1, first cycle you fetch, right? And then you decode the instruction 1. While you decode it, you can fetch the second instruction. You execute here, memory and write back. Fetch, decode, execute, memory and write back. And I hate PowerPoint that try to like fight with me on drawing these things. Fetch, decode, execute, memory, write back. Fetch, decode, execute, memory, write back. So how many cycles does it take to finish this full instruction? Let's look at the diagram and how many cycles, show how many cycles does it take. 8, right? 8. So now let me do another example. What if I have a multiply and load, right? And there's only one multiplier and it does take 5 cycles. Does take 5 cycles, right? How many cycles does it take? So let's go do that example, right? Fetch, decode, multiply take 5 cycles. So I'm going to execute for 5 cycles. Fetch, decode, and I have one multiplier, so I can't use it. It's like the washer and dryer problem. When can I use the multiplier? When can I use the multiplier? Which cycle? Cycle number what? 7, 8, 9, 10. After cycle 7, right? That's when multiplier is free again. So at cycle number 8, I can execute, memory, and write back. Now, this is the funny part. I can fetch here. Can I decode on the 4th cycle? Can I decode on the 4th cycle? What occupy the decoder at cycle number 4? Yeah, instruction 2, right? It occupied the decoder. So this is when I can decode, I can execute, because it's XOR, it's not a multiply. But then the memory is occupied by instruction 2 again, so I can do memory here, right back here. I can't even fetch because instruction 3 occupied right now, so I can't do anything until here. And then I can decode, I can execute. Again, memory is occupied, so I can do memory and write back right here. So how many cycles does it take for me to finish this? How many cycles in total? It takes me 16 cycle, right? Oh, why is the decode on cycle number 8? Think of it this way. You have only one decoder. You have only one decoder. For instruction number 3, even though I fetch at cycle number 3, right? I want to decode, but at that point, who occupied the decoder? Who have been occupying the decoder starting from cycle number 3? So that's okay. Yeah. So the instruction number 2 occupy the decoder, and it doesn't free up the decoder until cycle number 8. So that's when instruction 3 can start decoding at cycle number 8. All right. So it is more clear now. Yeah, so that's one thing. Another question is why are there 5 E's on instruction 1 and 2? Because I said earlier, assumption this thing takes 5 cycles. Basically, I said multiplier, the actual part where you have to execute the multiply does take 5 cycles. So I have to wait 5 cycles to finish. So is it more clear for both of them? For both of the questions? All right, awesome. So now do you see, hey, this thing is is not always perfect, right? We call these incident where you have to wait. These things, we call this instruction stall. It's like when you have a traffic jam, you can't go, you can't move forward because that's the guy in front of you blocking the way, right? So this is called instruction stall. And there are many things that can stall your instruction, but the fundamental concepts behind what happens when you have instruction stall is you basically don't have enough resource to move an instruction through the pipeline. So what are the effects? As you can see, I have to wait. I can't fetch the new instruction, right? So what can be the case here? The first thing that can happen, functional. You don't, the first thing that can happen, sorry about the typo, you can run into the case that you don't have enough functional units. Earlier on, the multiply takes 5 cycles and you only have one multiplier. So the second multiply has to wait for the first multiply. This is the same as the washing and drying machine. You don't have enough dryer, right? So for the washing and drying machine example, if you have the money to buy a washer, a new dryer, or hires your friend to help folding the clothes, which one would you pick? Do you buy a washing machine? Do you buy another dryer? Or do you hire your friend to help folding the clothes to make sure you can finish those 5 batch of dirty clothing and wash it and clean it in as fast as possible? Which one do you buy? Yeah, probably the dryer, right? Because now if you have 2 dryers, while you're waiting for the one of the dryer to finish, you can fire off the other dryers and finish the second batch. If you draw the diagram again, you'll see that it does take fewer number of hours and minutes to finish now the 5 batch of clothing, right? So this is what happens when you don't have enough functional units. And sometimes the steps can take longer. Think memory, right? Think of the memory. Anyone want to take a guess how long does it take to go to DRAM and access something over there? It can take 12 to 15 nanoseconds. That's a lot of cycle. 12 nanosecond is like 50 cycle. 50 nanosecond is like close to 200 cycle, right? So accessing the memory would take a long time. That's why you have the cache. That's why you have the cache so that you can quickly access something from the memory. You can have the unbalanced design. I have 10 adder in my machine. I have one multiplier. If you have multiple multiply instruction, you're screwed, right? So what do we do with these instruction stall, right? So first of all, you need to ensure the correct results, right? And make sure the pipeline register output the right value. We are not going to go dive deeper into the design, but we will name the design, right? When you add more functional units, for example, we call this superscalar architecture. Let's come back to this case. Can we add more multiplier? Can we have, instead of one multiplier, I just add one more. I can do now 2 multiply at once. Will my program get faster? Yes or no? Yes, no, yes, no. Will it be faster? Is it going to be faster if I add one more multiplier? The answer is yes. In this case, for this program, it's going to be faster. And the concept behind superscalar architecture is basically we can add more of these units in the hardware so that they can process new instruction kind of almost in parallel with the older instruction, right? Again, the processor should be balanced. You don't want to add like 10 or 20 multipliers and one adder. It's probably not a balanced design. It allows you to fetch more, decode more, execute more, and that's when If you look at modern CPU design, you can do like 3 to 4 instruction per cycle or more. That's when you can actually run billions or 10 billions of instruction within 1 second. All right. We call this instruction level parallelism. This is a little bit too advanced. It's kind of like jumping into more like a graduate level material, but this word is something that's so important to performance, including if you want to use the GPU, for example, to run a program. It exploits instruction level parallelisms. It's the ability that you can run multiple instructions in parallel, almost like a multi-threading. All right. So let's look at the other cause of instruction stall. First of all, if you have to access the memory, that would take a long time. So we will discuss this in lecture 5 to 7. We will keep this topic and we'll discuss it in the future because this is a big thing, right? But what else? You can have branch misprediction. And we'll also discuss this in the future as well in lecture 5. We're not going to talk about branch right now. So these are the two things I want to get out of the picture first, but kind of like prime you for what's coming next. If you have something in the code that looks like this. Your computer actually predict before you finish this part, it predict which direction you're going to, and it would actually actively run what goes in there. So it can guess, educated guess, basically to say, hey, it's going to be false, so let's go in here. Or hey, that condition is going to be true, so let's start this part of the code. Your CPU actively do this as well. Note that this is done on the CPU, not done on the GPU. All right. So that's also branch misprediction that can slow things down. But now, right, I'm going to go into the third thing that can slow things down. That's called the data hazard. See, you remember your comments earlier that like this is like a goal this like a mine for minefield for like deadlocks. Remember that? So one of your friends make a comment on the chat saying, hey, it can actually create a lot of deadlocks. It's actually not exactly deadlock, but it slows things down. Right? So you can have instruction stall that looks something like this. Anything you notice in the colored register name here? So in this case, let's assume I do R1 multiplied by R2 and write the result into R0. Over here, I do R0 multiplied by R4 and write the result into R3. Over this, I do R3 XOR with R7 and write the result into R6. Over here, I basically take R8 and write it into, oh no, not take R8. Take whatever is in the address 0x0AD, write it back to R8, and over here, I'm going to take R6 and add that with R8 and write the result into R0. What's the big problem here? What's the big problem here? What's with the color, like the red, the green, the orange, and the blue? Somewhat, yes. So the comments say might lead to weird data going places. If you look at pipelining, when do I know the correct version of R0 in this case? Let's finish the first multiply. When will R0 get updated with the correct results? So let me draw this table, right? Fetch for the first instruction, decode, and let's assume multiply now take one cycle. Let's not do the multiple cycle anymore. Fetch, decode, execute, memory, and write back. When will R0 get the updated results? Is it at cycle number 3, or is it after cycle number 3 where we finish the multiply, or is it getting written over after cycle number 5? After 5, right? This is where you write to R0. And this is basically where you know what R1 multiplied by R2. You know it right after cycle number 3. But then you have to wait until cycle number 5 to write it back to R0. So if I want to do this, fetch, right? I decode. When can I execute the second multiply? I decode and say, hey, I need R4 and R0. When is the correct version of R0 becomes available in the register file? You need to wait until cycle number 5. Everyone see this? Anyone confused by this? So you have to execute here because R0 never is available until cycle number 5. And you stall for 2 cycles. All right, with me so far? With me so far? Now let's do the next instruction. Fetch, decode. You can't even decode, to be honest, right? Because you have to wait. Decoder is occupied. Decode. And at that cycle, when can I know the value of R3? This is write to R3, right? So you can execute right here. Again, wait for 2 more cycles, memory, and write back, right? And this is where you can fetch, because fetch is open up again. Decode is now open up again here. And then this is the point where you know R6. Can I execute? Does instruction number 4 need R6 anywhere? The answer is actually no. I can do it now. Right? Because instruction number 4 is basically generating R8, but it doesn't require anything, so it can go to the memory right away. Now over here you can fetch, decode, and then this both need R6 and R8. It needs both R6 and R8. I know R6 after cycle 11. I know R8 after cycle number 12, so I can execute it right here, memory, and write back. Do you see how I have to wait quite a bit to finish each of these instructions? We call this data dependency, or sometimes we call this data hazard. Same name, same meaning. It basically means that my next instruction depends on the result of the previous instruction. And we can classify this a little bit, right? That happen, right? If you look at this, there's a dependency between each of the registers that generate the input into the next register. And this is really, really common in the typical program, right? Is it common here? How many of you do something like this? Let's do int A. Let's just basically swap two number. Let me read line of code in C that swap to three number in temp, right? How do I switch between A and B? I want to swap the value of A and B. I would do temp equals A equals B equals, right? And you see that this temp generate the result for this is right. So you have this data dependency quite everywhere in your program, and to leave it like this, it can slow down your computer. It can slow down your computer, right? And there are multiple types of data hazard. The classic in the 5-stage pipeline, we call this true dependency. It's basically I need to read something after I finish writing in the earlier instruction. It is called raw data hazard, read after write. In modern processor, there are two more where it doesn't happen in the you learn so far. This happened only with modern processor in a CPU, where data in a more of a data flow manner. You can have write after read and write after write. In an in order pipeline that we learn, right? Oops, you're not doing this. You're not doing this for a different class. My bad. In an in order pipeline, only the raw hazard exists. And to deal with it, the one way you can do this is shown you earlier. We can stall. Stall is basically insert a bubble. Somehow you read text, you call this insert a bubble. But basically, I wait. I wait until the data becomes ready, right? So I'm not executing anything. I'm gonna wait until my data becomes ready. And this is gonna be slow, right? So can we do better? We can do better by doing what we call data forwarding. So let me look at this diagram again that we draw. Right. And unless say I'm focusing on instruction number 2, let's say I focus on instruction number 2 right here. Let me ask you again. I know that R0 finish and get written by the time cycle 5 is over, but can I be more aggressive? If there are results into R1 multiplied by R2 somewhere in my pipeline, is there one? At what cycle, if I look at instruction number 2, at what cycle does the value of R0 becomes available? It's at cycle number 4, right? Right after the execute stage, I know what's the value of R0. I just have to wait until the write back, but the value is available. So now, because I know there's data right there, I will modify my design so that I do something we call data forwarding. What does forwarding mean? Can someone tell me the definition of forwarding in English? What is the definition of forwarding in English? Is to pass thing to another entity, right? So in this case, we pass the value of R0 from the pipeline into the input of my second multiply. And let me go back to the diagram, right? So actually, let's do the inserting the bubble first. So this is stalling, no forwarding. This is a slow solution, right? I have multiply R1 multiplied by R2 write it to R0. And this guy needs R0. Execute, generate R0, decode, need R0. The next cycle, I let this move on. The multiply move on. This instruction stay here. I say, hey, I need R0. And this is not doing anything at this time. The next cycle, multiply, move on again. I'm not doing anything here. I still say I need R0. Then I finish write to R0. That's when I can move this to here because I now have R0. So that's inserting the bubble. The reason why we call this bubble is because over here, we kind of bubbling the nothing, like nothingness. Bubble contains air. There's nothing inside. So we insert the bubble into the pipeline. The pipeline doesn't do anything because I'm waiting for the data. And I can actually check, like I can build an if-else statement to check when do I have to stall, when do I have to insert the bubble, right? Basically, if I need the value of my previous instruction in the pipeline, I stall, right? And I'm gonna stay in my decode stage until that data is written back. So if you want to write this in a big giant if-else statement, here's what it is. If I need to use anything in the source, right? I need to use anything in the source that is generated by, so this is need to use some value. This produce the updated value. Then you stall. You insert the bubble, right? No need to memorize this, but you can actually take this class and put it in the processor design language, just like a multiple hardware description language, and use this to actually make sure you stall the pipeline at the correct places. No need to remember this particular site. It won't go on to your exam. You need to know the concept. All right. And stalling, if you kind of do the analysis, you realize that the time you need the operand is in the decode, right? This is where you need the operand. R type is register. Load is anything to do with memory that are reading. You read from the memory. This is you write to the memory. Branch jump is basically trivial, as the name suggests. This is where you generate the new value. So it's safe to resume the instruction whenever the value becomes available, right? Whenever the value becomes available. And now I talk about data forwarding, which is what we covered earlier, like where, hey, R0 multiplied by R1 is available after the multiplier. So you can actually do this. Data is available either from the execute, or if you have to go to the memory and read something, is at the memory stage. So why do we need to wait until the write back? We can forward the results that are in the pipeline to the future instruction that are also in the pipeline. So for each instruction, what you have to do is, do I need something in the pipeline? If yes, forward that. If no, keep executing. This solve read after write dependency. Because if you have to write into something, you can forward that and feed it to the operand, right? The benefit is faster. And here's the example, right? Here's the example. Let's say over here is multiply 0 multiplied by R1 and write the result into R2. Over here is multiply, and I want to do R1 multiply by R2 and write the result into R3. Is there a data dependency here? Is there a raw hazard here? And someone answer me, is there anything that would generate data dependency? If yes, what register generate that problem? R2, right? R2 need to be generated as an input to the next multiply. So if I'm gonna circle something, let me somehow zoom into this wire at point number 1, this wire at point number 2, and this wire at point number 3. What point in that wire would have my result? Is it number 1, number 2, or number 3? Number 1 is coming right out of the multiplier in the execute stage. Number 2 is somehow in the earlier instruction. Number 3 also from the earlier instruction. Which one have my value? Which one has the correct value of R2? If I just zoom into these 3 dots here, from 3 different stages, one from execute, one from memory, and one from write back, which one has the correct value of R2? So the R2 that has the correct data is here, right? It's in the number 1. This is when R2 is updated, because that's the instruction in the pipeline here, right? So by that point, I have the R0 and R1 in my multiplier, right? And multiplier would generate R2 for me. So at that point, that's when I have the correct value of R2. All right, with me, so is it clear or is it confusing? Anyone confused by this? Anyone confused? This basically has R2. That particular virus has R2. Yeah, sure. So now we have 2 instructions. The one in the execute stage is doing R0 multiplied by R1, right? Which means that this wire right here has R0 multiplied by R1. Is it correct? Because I have R0 and R1 into multipliers. I'm multiplying it right now. It's basically generating R0 multiplied by R1. So with me so far? Yeah. And the next instruction, we know that we need R2. And we know that this is basically R0 multiplied by R1, right? From the earlier instruction. Because there's data dependency, right? Which basically mean, I mean, I'm going to use the different colors to reduce confusion. Which basically means that I can take whatever signal from here. Let me stay in the execute stage and kind of, I'm going to take this value and I can now feed it here. So in the real design, it's actually like wires coming out, feed that into the decoder. I mean, in the decode stage, pipeline register and say, hey, well, that's the forward path from the execute stage. In this case, it does have the updated version of R2 that you can use. Are you with me so far? Yeah, so basic, that's it. Now, let me, if you are clear on this example, let me confuse you a little bit here. And now let's say, hey, there's some add something here, doesn't matter. But now my multiply 0 multiplied by R1 into R2 is actually not in the execute, but in the memory. Basically, these generate this. So in this case, between point 1, point number 2, and point number 3, where can I get R2? Where can I get the correct value of R2? So let's say this is add R4 plus R5, write this to R6. What does 1 have? What value does it have here? And what value does the number 2 have here? This number 1 is going to have the value for R6, right? And over here, number 2 have the value for R2. Is it clear in this particular case? You have multiply, add, and then multiply again. So in this case, you want to forward from this point as an input here. All right. Any questions so far? Any questions so far before we wrap this up? So that's actually it, right? So data forwarding provides you the ability to basically forward the data as soon as you have it. The benefit is clear. You don't have to stall. It improves the performance. It actually does improve performance quite a lot. The downside of this is actually now things get more complicated again, right? It gets more complicated again, but it's worthwhile. It's actually worth the price you pay. Every single CPU that you buy, at least most, if not all, will come with pipelining, data forwarding. It's actually so important to performance that it does have all these components. But if you say interest in architecture, right? And you have to design data forwarding for the first time. I mean, the next time you have to do it, it's not that bad. But when you have to design this for the first time, you will realize that, hey, this can be complex because input coming in can come from many sources, can be from this wire, that wire, that wires. So you want to make sure you connect to the right component and put in the right control. And then consider you have to do this for a 30-stage pipeline in like modern processor. And we haven't even talked about branch. We haven't talked about branch. So we will talk about branch and data load in the next few lectures. All right. And we'll kind of wrap up some of the things that we cover and kind of talk about future technology toward the end as well. That's it for today class. I was planning to release another in-class exercise, but I figure I would rather have you look at the P3 and then we do the next in-class exercise in the next lecture on Tuesday. So that's it for today's lecture. Any question before we adjourn? Great question. For now, no. Until we cover caching, which is the next lecture. Yeah. So for now, it doesn't really relate to the project. And again, you can also check with your friend who start the project already. You can start it now. It's actually pretty easy. It's actually pretty easy. And you don't need much on top of knowing how to program in C for many of the earlier tasks. For the later tasks, if you know caching from system skill, that's all you need. All right. Any other questions? Next week, I think one thing that may be good for everyone here is I'm gonna cover before we finish the class. I'm gonna cover what is needed. I'm gonna cover matrix multiply. I'm gonna cover block matrix multiply a little bit. Would that be helpful so that you can, if you want, you can like finish the project right away. Otherwise, that's it for the class today. We'll see you all on next Tuesday. All right.